All right. Hello, everyone. Good morning. Welcome to the second day of the great CS Research Week. It's my great pleasure to introduce Professor Xiang Wang from UCSB. It's a great pleasure to have Xiang here, not only because of his great achievements and impactful work in the areas of statistical machine learning, data protection, and responsible AI, and his recognitions, Best Paper Awards at KDD, AI Stats, COLT, many faculty awards from Amazon, Google, and others, but also, more importantly for us, because he is as our alumni. So it's a great pleasure to have you back. He finished actually his studies at NUS and went on to do a PhD at CMU. Right after finishing his PhD, he visited us. I vividly remember the discussion here, and so it's a great pleasure to have you back. Thank you.
It's my huge pleasure to be here. Like Riza talked about, I was an undergrad here at NUS. I was in the ECE department. That's my library card. Obviously, I studied a lot for me to keep this for this many years. Yeah, I don't look a lot like what I was back in 2007, but maybe that's also because I studied a lot. So it feels a bit surreal to be on the other side of the podium now and telling a story about the research program that we've been developing the past couple of years. And when people sitting in the audience could be people who I learned intro to programming years ago. So today's talk is going to be like watermarking of generative AI in the generative AI era. So this is joint work with my student Xuan Dong and also UCSB student Ke-Xun Zhang, and my colleague Lei Li and Praben Zhang. I'm gonna. This is what I'm gonna do today. I'm gonna first motivate the problem by why do we need to watermark AI generated content, and then I'm gonna break down 3 recent pieces of work that we've done. In different aspects of watermarking AI and AI-generated content and AI models. Okay, so the main focus will be on part 1. So we'll see, since this is the extended format of the talk, I'll see how much we can do to cover the rest of the topics. Okay, so everybody has used ChatGPT, right? So it has taken the world with a whirlwind since in the past year. So there are several of them from OpenAI, Google, and Anthropic, and so on. There are also these open source versions based on all kinds of cute animals. I argue that the large language models are extremely useful for many reasons. We can use it to solve problems. We can use it to generate blog articles. Help us with pair programming, use copilots, and so on. But most importantly, they're kind of useful for all kinds of making our life as a professor a lot easier than before, right? So there are some legitimate use cases like this, but there are also somewhat shady use cases that prevents the students from learning anything. Right, so we want the former, if it's able to generate the good questions, but we don't want the students to just solve the problems without actually having to go through the process of problem solving. So they don't learn anything. And the large language model can have a lot of malicious use cases. Like now it becomes increasingly easy for scammers to scam your grandparents by putting together a chatbot and pretend to be someone they know and then get money from their bank account. There are issues like this that has already started. And in addition, this AI has been making fake news and by creating images and text with malicious content, significantly more cost-free than before. Right? So the big question, the million-dollar question is that with all these issues, is there like a silver bullet that we can solve everything once and for all, or at least like 80% of all these misuse of AI? So what can we do? So there are a few obvious solutions. The first one is, can we just come up with a detector that can simply solve the Turing test, right? Given a piece of text like this. Yeah, so I encourage everybody to read this, text, and then maybe take 5 seconds to read this. And can I have a show of hands who think this is written by a machine? Please raise your hand. Okay, just a few. Who thinks this is written by a human? Okay, similar number, so other people are shy. Yeah, so this is actually like the first paragraph of Wikipedia. It's written by a human, or maybe I misremembered. But the point is that it's somewhat difficult to tell just directly from the text itself whether it is written by AI or not nowadays. So one possible solution is that we can train a machine learning model and feeding a bunch of input-output pairs, and these are all the text that's generated by AI, and these are all the text that's written by human. And then the machine learning model is able to, so it's very good at this, right? Picking up the statistical signal and tell apart very subtle differences between two distributions, and then predict really accurately. So we can train a machine learning model to solve this test, and it's going to do a lot better than a regular human being is able to do typically. But on the other hand, such ML-based approaches is statistical intrinsically. So all it is hoping to do is to witch hunt for statistical patterns that are specific to individual distributions, and it becomes very non-robust. Right? When the distributions start to shift a little bit, for example, this is an example of this called Detect GPT. That were created for the particular purpose, and then when people use it for non-native English speakers, and it starts to make a lot of false positives. It starts to so there are I think 6 of the different ML-based detectors for AI generated text, and you can see that. So even though these methods they work really well, in general, but when you putting the TOEFL essays and ask it to detect, and more often than not, then it is a false positive. It predicts it to be AI generated. So the quality of the text and other kind of a subtle distribution shift has a significant impact in the performance of these methods. So all machine learning models, they only work on average when the test data has a distribution that are very similar to the training data. And in the really high dimensional space of the written texts and articles, it's just impossible for the model to perform well when the coverage of the test data in the training data distribution is not good. Okay, there's really no way around this. But there's this second possible solution that instead of witch hunting for statistical patterns that's intrinsic in the distributions themselves, what happens if maybe we can plant the statistical patterns ourselves, right? We can try adding what we call a watermark into these texts so that later we can retrieve that very much in the cryptographic sense. Okay, so here's an example of an image watermark, right? It's pretty obvious, right? But what is the kind of problem, right? Suppose we use this type of watermark to just label this image as being AI generated. Anyone? Yeah, you can simply use Photoshop to erase the watermark altogether, right? So these are what we call the visible watermarks. But there are a bunch of other things. Actually, there are loads of academic research and the social literature for many years on coming up with watermarks that are subtle and invisible, that's intrinsic in the images themselves. Yes, there's a question over there.
Yeah. Are you suggesting that the adversary is going to be able to, the way I understood is that the adversary is creating these chatbots, right?
Right.
How can we control the process of creating chatbots
Yeah. So that's a very good point. Who has access to what? Who has control over like which component of the generative AI pipelines, right? So I'll get to this, but the high level idea is that there are a few big players who can afford to ship the state of the art generative AI services. Right? And everybody is using that, and there are regulations that require some kind of precautions and measures to be done to kind of inject the watermark. Right? So that's more of a policy issue and more of a social choice problem. But then in this talk, I'm going to focus on the technical aspect of how do we actually inject watermarks in the text to begin with.
We are the people who want to inject the watermark. We are the chatbot.
Yeah. We are the service provider. We're trying to somehow modify the generative AI. But there could also be like this post-processing type of watermark that you can say add to the image that's already generated. Okay. Yeah. So back to this slide. So there are a lot of like existing work on injecting watermark to images. So least significant bit, which takes every pixel and then modify its value by a tiny bit systematically, right, using some pseudo random function. So in this case, if you know the security key for the pseudo random function, you know exactly what the least significant bit should be, like given the location or the neighborhood of that pixel. And then it's not going to affect the visual quality of these images at all. In this example, you can see that on the right-hand side, on the right-hand side, so that's the difference between the watermark and the unwatermarked image, and it's amplified by 100 times, if not 1,000 times, for this to be visible at all. Okay, so these kind of watermarks are called invisible watermarks. So I'll get back to the invisible watermarks later. But yes.
But here the model is that the attacker doesn't know that watermark is there, because it will be easy to remove to change the least significant.
Yeah, again, like these are just high-level ideas for now. I'll get to specific details of what the model for the adversary, like what it has access to, just in a little bit. Okay, but the more interesting question to address right now is that what about like where we're dealing with text instead of images? Right? So text doesn't have a least significant bit, right? So it's an intrinsically discrete object that if you change a word from one word to another, it changes the meaning of the sentence like almost altogether, right? So it's somewhat difficult to replicate the same ideas from the images and insert these statistical patterns for the text. Okay. Despite that, there are a few possible things that one can do, right? So here's the one of the say more obvious watermarks that you can add. You can append the sentence. So any legal reproduction of this content. In this case, this is a Tang Dynasty poem by Li Bai, and if you use it and reproduce this, the content will result in immediate legal action, right? But it's not very reassuring, right? So why is that the case? If you post this online, right, people can simply take it and then remove the disclaimer and then just put it elsewhere, right? It's easy to just get rid of the watermark altogether. So here's another attempt. Instead of doing things explicitly, you can insert some secret messages in the text themselves. Can anyone tell me like what the secret message over here is? Yes. Exactly. Yeah, if you highlight this, like it's telling you that if you just read vertically of all these words, you get this secret message that's embedded in this text, right? So you can do something like this by generating like a particular way of rendering the text such that they encode the secret messages that are not completely obvious to people, and it's also not obvious like how you can easily remove this. But there are other issues, right? With like simple shifts in the location, with some modification to the text, right? You can destroy the the message altogether. Right, so that's another problem that needs to be solved. It needs to be secretive, but it also needs to be somewhat robust and resilient to edits and modifications. Okay, so let's take a top-down approach by thinking about what are the desideratas of designing a good watermark. Right? So what are needed for the watermark to work well and to satisfy the practical needs of detecting generative AI? Okay, so first of all, like we want the generated text to have high quality. So in a sense that, so suppose we modify the model a little bit to generate a different text comparing to suppose I use the model, the language model to generate the text without the watermark. The quality of these two pieces of text in terms of their distributions should be somewhat similar. Because otherwise, nobody will use your service, and they will just go to the next door, the open source ones, and then get something of a comparable quality. And then we want provable guarantees. We're hoping that the watermarks, if the text is not being generated by the AI, if it is the watermarks not injected, then we shouldn't detect it as it's being watermarked, right? So that's the type 1 error. Also remember this as just a false positive rate. You want the false positive of your classifier of detecting AI to make no mistakes. And we also want type 2 error bounds, which says that if the image or the text is indeed watermarked, then you should be able to retrieve it correctly with high probability. So in this case, we call this only true positives or having a bounded type 2 error. So both these errors should be, we should be able to make them arbitrarily small by choosing the parameters of the watermark. And sometimes under additional assumptions on the generated text being, in some sense watermarkable. Right, so there are cases where it's not watermarkable and it's unclear what are the right way to go, and I'll explain these subtleties just in a little bit. And in addition to that, like as I alluded earlier, like we need some kind of a security property, or also known as robustness property. We need these watermarks to be robust to all kinds of evasion attacks. Yeah, these, in my opinion, is the most important properties that any watermark that's useful in practice needs to satisfy. Let's make it slightly more formal, right? So a watermark is two functions. The first function is a watermarking function. So this watermarking function takes a language model, this big categorical M, and creates a slightly different language model called I'm hat. Okay, and then anything that's generated from I'm hat is considered watermark. It changes the distribution of sampling the next token for the language model using some possibly random detection key K or secret key K. And the second component of a watermarking scheme is a detection function which takes the knowledge of this secret key K and takes the already generated text. And the correct behavior is that it should be able to output 1 if Y is indeed generated, or if Y is indeed generated by I'm hat, and you should output 0 with high probability if Y is not. Yes.
Do you really want the key to be secret?
Could you say it again?
Do you really want the key to be secret?
Do I really want the K to be secret? Yes, that's a very good question. So there are public encoding schemes where anybody can inject a watermark, but only like a selected field can detect and retrieve. There are other cases when it is better to keep K secret. For now, everything that I'm going to talk about will focus on situations where K is a secret.
Coming back to the example that you presented.
Right.
Somebody like me is trying to detect, in order to get, not get scanned.
Right.
I'm trying to detect whether this is generated by a model of this type, right, and prime. Then I must know the key K. And if I know the key K, being a normal user, like a public person,
Right.
then everybody must know. It's not secret.
You can maybe you have like other kind of access, right? Maybe you have a service where you can put in Y and it's going to tell you whether it is detected as, you can do fancy learning and use it to try to recover K, which is something that I'm also not covering in this talk. But yeah, these are very, very interesting questions, and which is also the reason why like this research area is just growing amazingly quickly in the past year. And I think now there are more than 100 papers in this domain, right? But the big problems are being solved right now. But there are also a lot of extensions and issues that you can define your own problem and solve it in specific ways. Yeah. So at the moment, the detection key is only known to people who have access to the detector, and people who can, like this is a service provider. And the service provider can decide to provide this detection services to the university, so university professors can detect the homework submissions. It can be provided to the funding agencies or other high-stake environments. But if you make this K generally available, and then there could be additional issues that needs to be addressed.
Right, but I think this distinction is very important because if I'm controlling the generation of the content to embed a key, and I'm controlling the detection process itself, then there are existing cryptographic schemes that will just satisfy this. Right? I just embed some secret bits in the text, and I should be able to go back and check where they are.
Yeah, there could be things that could work, but there are very interesting other considerations to the watermarking problem that everything needs to be carried through a discrete sequence of tokens Y, right? That prevents some of the standard protocols to be used over here.
Sorry, just a quick question. Is it, of course, it's nice if M hat is also an LLM, but
is it required?
Would you need it? You just output something else. So you start from M.
Yeah, it's a generic function. Yeah, it's a generic function. Yeah, and then M hat is also random because the detection key is random. Yeah. Okay, so there are several parameters that we need to work out to determine the properties of any watermarking scheme. So we call this omega quality of the watermarked output and alpha beta correctness of the detection. So we say that the watermarking scheme produces M hat that satisfies this omega quality. It means that some kind of a probabilistic metric, like this divergence of P hat and P. So P without a hat is an unwatermarked original language model. P hat is a generative distribution of the watermarked language model. And the difference is this is the distance between two, or divergence of two distributions should be smaller than omega, right? So omega, we want it to be some kind of a small number. And alpha beta correctness is just a parameterized type 1 and type 2 error. So there's the specific thing that I wanted to highlight is that in this, when things is not watermarked, it can be really arbitrary. It doesn't have to be generated from the non-watermarked language model. It can be written by me, it can be written by you, it can be taken from elsewhere over the internet. So the only requirement is that it is statistically independent to the secret key. Okay, but when things are being watermarked, this is more specific. Because it needs to be this very specific thing that's generated from M hat, drawn from a sequence of distribution in the rollout from P hat T. So I'll talk about what rollouts means and what these language models are, but I'm just throwing these definitions out here so you know the notations and you understand what are the considerations that we need to design this scheme. Okay, so the most the last property of interest for the watermark is the security property. So in this case, we want the any watermark text to be robust to perturbations, to some kind of perturbations. so assume there's an adversary. Excuse me. Under a model of adversaries, observations and ability to modify and post-process the watermark-generated text Y into something else. Let's say that after the post-processing becomes Y like subscript A, And we hope that this detection procedure can take this already modified text and still output the same output the same 1 or 0 as if as if the edits or other kind of modification weren't there. Right? So there are many different ways of defining what this adversary can do, but the simplest and the most natural way, like for the first work in this domain, in our opinion, is to define this to be the bounded edit distance. So the adversary can have arbitrary information, can do whatever she sees fit, but edit this sequence, suspect sequence y into some y underscore a. Right? And the modification is bounded by this parameter eta, and then we can try to characterize this parameter dependence of the parameter eta to the original language model and properties of original language model and the specific generated text. Yes. Yeah, excellent question. So the question is, does the detector have access to the original language model? It could, but in practice, you shouldn't assume having access to the original language model for this to be, of any use in practice. And even if you do have access to the original language model, as well, I will explain, it might not help you in any way at all. Okay, so the idea of a security property is that it needs to make enough edits in order to evade the detection. So you can think about this edit distance to be a surrogate for the amount of work that the attacker needs to perform, right? So obviously, if the attacker just replaces the whole thing, then nothing can be detected, and it's unclear whether it should be detected as being watermarked at all, right? On the other hand, if the adversary only changes a few tokens, say a constant fraction of the tokens, then we should expect the method to still work and not detecting this as AI generated or not.
So the attacker can always make changes.
Yes.
Right? And because this is language,
right.
The attacker can totally transform the text always, and then the detector will give you 0, right?
Yeah, exactly.
Let's take a trivial technique is that you take the text, you run it through a translation,
right, and then translate it back, right?
The text will be most likely all completely different. Right?
Yeah, that's a more advanced attack, which we call a translation attack or paraphrasing attack, right? So this kind of attack is.
But that can always be done, right? So you could always escape it.
What happened is that even in those cases, since the translation and the paraphrasing services doesn't really know the secret key, right? So in practice, what we observed is that the watermarking scheme that we came up with is still pretty robust towards the translation and paraphrasing attack. So that's one of the punchlines that I'll cover. Right, but our theoretical result is only able to cover the edits model. And in this case, it's adversarial modification model. And if you assume the knowledge on the adversary on what information that they are able to draw to come up with these edits, then they can be more robust. And there are subsequent work, not from our group, that works with that slightly weaker models.
I think the point was that if you look at censorship,
right. Right. I'm fully aware of all of these attacks that's out there, and I'm going to give several examples about the different kinds of attacks people can come up with and how our watermarks are sometimes robust to those in theory, and in other cases robust to them in practice. And in many other cases, not robust at all. Right? So it's not a solved problem at this moment. In this case, adversary can actually even know the K. Yeah, but
for any adversary, right? Definitely at least an adversary who can, but if you know the K.
Yeah, but then the adversary still needs to be bounded by the edit distance constraint. Yeah, so it's,
If the edit distance is like adversary attack, even you have the edit distance, you can find something.
yeah, you can find something that's within the edit distance, but then in order to satisfy these properties, then detection should still work, even if the adversary is fully adversarial and know the key. Okay? So the robustness is like really the most important property for all of the reasons that you guys has been like kindly bringing this up. So the students won't really use the generated content verbatim when submitting the homework solution to the professor. Like they will pick and choose the different parts of the generated content by cropping, shuffling things around, and edit things and improving the quality of the text by moving things that are no longer relevant. Right? So things can get really, really subtle. But any watermarks that works in practice will have to be somewhat robust to many of these like intentional or non-intentional modification, post-hoc modifications to the generated text. Okay, so that's the motivation of having those properties. And there are two other properties that are often needed. One is computational efficiency. Right? If so large language model is so expensive nowadays to run inference on. If you are twice as efficient as the current non-watermark version, then it's not going to get shipped. Right? It's not going to get used at all because it's additional cost for the company to use this. So it only needs to be, it needs to be like 1 plus little 1, right? Type of additional overhead. And moreover, like this goes back to the questions of whether the detector have access to the language model. So even if you have access to the language model, since you don't have access to the prompt that the student used, there's no way that you can invoke the language model to actually come up with a distribution that ended up generating the text to begin with. Right, so it's somewhat difficult. So in order for the detector to work, you can't make use of a lot of information that's available. You have to bootstrap from a particular piece of already post-processed text, and together with a secret key. Right, these are likely to be the only information that you can leverage to come up with the detector. Okay, so. Now let me backtrack a little bit and tell you what a language model is anyways before talking about the watermark on this language model. So language model is really like a way how you can come up with a sentence and based on what you have uttered so far and what is the next probability of the next word that you're going to say and you're going to write. Right, so you have a prompt, so solve homework 2 for me, and then the language model is going to continue to iteratively, recursively generate the solution by conditioning on everything that's been generated so far, and then sample from the distribution of the next token. As a quick example, so I'm going to ask you guys to try coming up with next token. So you were having a great time at a bar, and suddenly she showed up, and you said to your pal, hold my... Good. So, you sampled with a pretty good probability, hold my beer, but it doesn't have to be hold my beer. It could be other things. It could be, hold my gun, and it could be, hold my hand. It could also be other things, like hold my blood pressure or something. Right, so it's a full distribution over a space of vocabulary. So we're calling this all the universe of all possible words or tokens. This big V, vocabulary V, and the cardinality of this V is the size of the dictionary or vocabulary. And another thing that I want to mention over here is that when this, like sometimes the distributions that they're generating have many different options, and you have different choices, and each with a relatively small probability. In this case, we say that this distribution has high entropy, and in the cases when things are more or less deterministic, for example, if you ask the language model to just recite the Declaration of Independence, and it's going to do it correctly every token one at a time, and you will have 1.0 at the correct next word and 0 everywhere else. Right? So in some cases, you'll have no entropy at all. In those cases, we're calling this low entropy sentences to be generated. Right? And in the cases when you're asking the language model to recite the Declaration of Independence, arguably, like there's no hope that you can watermark the process while keeping the solution correct. Right? Because there's no other way. It's a human written it and machine written this Declaration of Independence. They're all the same. There's no information that you can inject. Maybe punctuations and spacing and other cosmetic things that you can do. But those are very easy to get around with like standard tricks. Okay, so we are not the first to study watermarking for language models. There are groups before us who studied this, and they came up with various interesting approaches for watermarking. So a group from Maryland, Kirschenbauer et al. So this is from Tom Goldstein's group. They came up with something called a green-red watermark. So it is a statistical watermark that changes the distribution by labeling some part of the text, some part of the token space as a green list, and then slightly increase the probability of the green list. Okay, and then they decide the split between green and red according to, say, the token before the current token to be generated. And there are other watermarks of more cryptographic flavor, say by Scott Aronson. So he didn't publish this, but he's been giving talks all over the place. So this is the most likely deployable watermark with OpenAI. So Scott came up with this idea of using what the machine learning people call the Gumbo softmax trick, right? By instead of sampling from the exponentiated distribution of the logits in your language model, you add a Gumbo noise to the logit. But instead of adding an actual Gumbo noise, you add the pseudo-random version of the Gumbo noise, where the pseudo-random function is secretly a deterministic function that depends on, say 8 tokens, the sequence of 8 tokens before the current token. There are many others that came up with the watermarking scheme that enjoys a different kind of property. So our contribution here, this is the fourth paper over there, is to come up with the first provably robust watermarks that enjoys a security property and also have type 1 and type 2 errors and so on, provably bounded with concentration. Right? By concentration, I mean that it has an exponential tail. Right? It goes to 0 very quickly as the length of the sequence to be watermarked gets bigger, and as the amount of entropy, right, in the sentence gets bigger and bigger. Okay? So what I'm going to do is I'm going to explain how our watermark works. Right? It is like a variant of the green-red watermark that I just explained to you. And then after explaining our results, I'll tell you how like our method compared to some of these other approaches. Okay? So the watermark we propose is called a unigram watermark, which really like statically and randomly partition the space of vocabulary into green and red. Right, those tokens labeled with green is this gamma times the V. So choose gamma to be 0.5. So half of the tokens are being labeled as green, and the rest as red. And when we generate the sentence, we take the original language model to come up with a logits vector. And logits, when you exponentiate it and apply the softmax transform, you get a probability distribution that you sample the token from. So the idea is that we'll choose this parameter delta, and we'll add a little bit of give the green tokens a little bit of advantage by making the logits of the green tokens slightly bigger, by increasing LTs if the tokens is green by delta. And then we basically apply the softmax transform and then sample from this p hat. It's really simple, right? It's the most straightforward thing that you would come up with. And it's also randomized, and when delta is small, you should expect that this watermarking scheme is producing something very similar to that of the original original unwatermarked model. Yeah, Hamid, go ahead.
What's the difference with the previous scheme by the Maryland people?
Yeah, so the very good question. So the main difference from the Maryland paper is this is so-called the unigram watermark, in which the red and green lists, they are chosen statically at the beginning of time. And in the Maryland work, they choose this green and red split according to the previous token, according to the by conditioning on the token before the current token being generated.
Oh, so it's fixed.
Yeah, so it's a fixed, persistent green-red list split.
I mean, you need to have like a secret thing on the UNO that doesn't work. Do you both require the same amount of secrecy? Like, you need a secret K that nobody else knows?
Yeah, the secret key is really the pseudo-random key that generate the green-red split. You can refresh that from time to time. You can choose a different key for different users.
Does the Maryland one require that to be kept secret?
Yeah, they also require it to be kept secret. And the difference is that their randomness in the secret key is a lot more than us. They basically multiply this by the size of the vocabulary. Okay, it's a simple modification to the Goldstein watermark. Yeah, we basically recursively sample from this distribution. So that's the watermarking scheme. As a quick example, just like before, so we are increasing the probability of the green tokens slightly, and these tokens are labeled green and red, and then you can see that the probability of the green changed a little bit, and the probability of seeing the red like decreased a little bit. But overall, they behave more or less like the same language model. So the second component is the detection, right? So the detection is also straightforward. So take any suspect text, y1 to yn, and then you basically do the z-scoring by removing the mean as if it is not generated by the watermark AI, right? The mean is gamma times n. And the randomness is over the green-red list split, and then you divide by the estimated standard deviation. So this should give you like a zy that is something like that looks like a Gaussian when it is not watermark. But then the mean should be significantly larger than 0 when it is actually watermark, right? And then the detection is simply a thresholding function at a predefined threshold tau, and this tau can be chosen as a function of y, and then return 1 if it is over a threshold, and otherwise return 0. Yes, Hamid?
The green list is more likely to happen. So you
Yeah.
see words from the green list more often in the text.
Right.
So if I look at the text,
Right.
and if I know what the green list, or if I see some words being repeated,
The green list tokens with a persistent watermark, that's a very good observation. The green list tokens are more likely to be seen relative to the language model, relative to the unwatermarked language model, and slightly. And if delta is small, and the amount that the green list is more likely to be seen is just slightly bigger. And if you know what the original unwatermarked language model is, you can more easily estimate it. If you don't, and if you just compare that to the marginal distribution of the human, then depending on how well the original language model is approximating the marginal distribution of a human generating those tokens, the error might be bigger or smaller than delta, right? So in our experiments, we found that we actually tried conducting the kind of learning attacks. But what we discovered is that it's still somewhat difficult if you don't know the language model to tell which tokens are green or which tokens are red.
you had this parameter omega in the beginning.
Right.
How is omega related to delta?
Yeah, I think maybe two slides from now. Yeah. Okay, so what really happened behind the scene is that once you have a sequence that's generated by this watermarking scheme, and if you know the secret key, you can label them as green and red, and then you can calculate the z-score and then threshold it. And you can also do statistical inference, and you can control the type 1 error to be arbitrary values that you like. Okay, so for the The watermark comes with mathematical guarantees that checks the definitions that I proposed at the beginning. So it enjoys the quality guarantees, the detection guarantees, and also the security guarantees in the sense that it's provably robust to arbitrary edits. And comparing to versions that depend on the prefix, and it is like significantly more robust.
So the results are asymptotic, right? Because this makes more sense as n grows larger. Do you have a sense of what?
Our results are finite sample, finite length. It's not asymptotic.
Okay, but does it do well on short text?
Like it needs to be like 200 tokens or so. Yeah, so it's pretty reasonable. Yeah. Okay, so back to your question about the quality. How is delta depending on how is the parameter omega depending on delta? So this is a result that we've gotten. So when you choose this delta parameter, then the distribution of the language model p hat and p in terms of any Renyi divergence with parameter alpha is bounded by the following. So even if alpha is infinity, in which you want a multiplicative bound, right? So this is bounded by delta. If you want KL divergence, then it is scales like delta square over 8, right? By taking the limit of alpha going to 1.
So delta was the addition to the logic.
Yes.
So in practice, you take delta to be like 1 or 2. Is it a small, very small, or?
If it is, I think if it is 1.0 or something, then you end up getting this 200, 150 tokens that will work. If your delta is smaller, then the length of the sequence needs to be roughly 1 over delta square, to be detected. Yeah. Okay, yeah. So how do we get this? For those of you who know differential privacy, so this is essentially sampling from. This is essentially an exponential mechanism. You're sampling from a exponentiated version of the utility function, and the utility function are the logits, and you're perturbing the logits a little bit. So there are two, neighbors in the differential privacy sense that differs by at most delta. So therefore, it satisfies this delta, in some sense, delta pure DP, but also like alpha delta square over 8 Renyi differential privacy. Was that the question that you were about to ask? Okay.
Since you partitioned the words into green and red randomly, there's a good chance, close to maybe 1/2, that the paraphrase, the synonym of a word, appears in the other cluster, right? So
Right.
Green, the synonym is red, right? So any perturbation of word by word would just perturb the distribution. So why don't you just consider that meaning structure between words when you partition? So for example, if some word is green, the chance that its synonyms are also green should be larger compared to some other words. Okay, would it make it more robust?
Yeah, that's a very interesting idea. That's about encoding more structures and knowledge in the watermark design. At the moment, we're not doing that, and everything that we got critically relies on the randomness of the splitting, right? But obviously, things like stop words, you can get rid of them, right? And some synonyms and others, you can sample one by condition on one of them and modify the. So as long as later you can retrieve it somehow, even after people have modified the text somewhat, then things will be better.
Are you going to show results on modifying the text? And
Yes.
see how the test results are?
Yes.
Does is the security affected if I get to see many examples of text that passes and text that does not pass, after you fix the key?
Yeah, that's a learning problem, right? If you see a lot of text with 1 and 0 labels being watermark and non-watermark, or green and red, then you can use it for supervised learning. So you can potentially learn learn the green list, right? So in that sense, the security is a concern, right? If people collude and get a lot of text like this, and then try to reproduce a language model and try to break the watermark, but that is a lot to assume. About people's coordination. So at the moment, we're not dealing with that problem.
And you could just change the key every now and then anyway.
Yeah. We can change the key every now and then. And as I've mentioned, since our type 1 and type 2 errors, they goes to 0 exponentially, then we can afford to do union bounds, right? We can afford to do union bounds and then have a bunch of secret keys and then choose one of them at random and then try to detect all of them. As long as one of them fires, then we end up detecting this as being watermark. Right? And we can also refresh things every once in a while. And we can assign different keys for different users. Right? And for user IDs, if we collect, then we can even like sometimes attribute the generation to a particular user section. So everything would rely on like this exponential tail that we will prove for this alpha and beta.
You haven't told us how the key works. Like, presumably it's a PR key.
Oh yeah. The key is very simple here. It's just a random partition of the vocabulary space.
Have you tested your detection on human-generated text? Do you detect watermarks in human-generated text?
Two slides from now. Yeah. So for now, let me first show you results on the quality of the generated text. So all these box plots are about the text perplexity. When we watermark GPT-2, OPT, and Llama model, you can see that as the model gets better and better, then the distance between unwatermarked and watermarked text. So the blue ones are human written text, and the orange ones are original language model without watermark. You can see that the distribution of the perplexity is somewhat similar, with the perturbed version being slightly worse, but it's like within they still cover each other. And in particular, when you compare ours with Kirschenbauer, this Maryland watermark, which is slightly less robust, you can see that on Llama is essentially indistinguishable in terms of utility. We also did the human evaluation and asked the human to say to compare like which generated text is having higher quality, and nobody can tell like which one is better based on say thousands of generated text that we show to the graduate students. Okay. All right. So let's go to the detection guarantees. So there are type 1 errors and type 2 errors. So in type 1 errors, this is a result that we were able to show. So let's say that the suspect text, the only assumption is that the suspect text is independent to the secret key and to which tokens belongs to the green list. Then we can prove that with high probability, this z-score is smaller than this quantity that depend on the diversity parameters of VNC max. So I won't really tell you what the VNC max are, but they measures I think L2 and L infinity of the cardinality, the realized cardinality of the suspect text Y. Right, so everything. So the only probability that's inside this inequality is the probability of generating the secret key. Right, so suspect text is viewed as being fixed and independent to K.
What is ZY here?
ZY here is a detection score over here. Yeah, and that I should also explain this optional pre-processing of Y. So you could actually pre-process Y by taking the unique operator. You can get rid of all the duplicates of the tokens over here. So that will help us to just change this C max and V and assign them to be just 1. Okay. And in type 2 error, so we need additional assumptions, and I'll explain these assumptions like in the next 2 slides. But the key idea of the type 2 error guarantee is that with high probability, if this sentence is actually generated from watermark language model, then the z-score is going to be bounded away from 0. It's going to grow as a rate of square root of n. So rather than being a logarithmic factor around 0. Okay, so kappa is a parameter that depends on the entropy, and another property called homophily. And you can also see that there's a e to the power of epsilon minus 1 showing up. So when epsilon is small, so e to the power of epsilon minus 1 is very similar to delta itself, e to the delta minus 1. So the scale of the z-score is proportional to delta, proportional to square root of n, and also proportional to the amount of entropy there is in the generated text. So go back to Hamit's question. So these two results suggest that the required strength of the watermark is roughly 1 over square root of n to detect generated sentence that's as long as that's of length n. Okay, so this is another figure that directly illustrates the z-score on different models and different data sets, and what the distribution of the z-score is for watermark and unwatermarked text, and for human-generated text. For human-written text, you can see that the detection score tends around 0, and for the watermark text is significantly bigger, right? You can draw a horizontal line here to threshold them to almost perfectly separate them. And in all of these sequences, we constrain the generated length of the text to be I think 200 or 250. So I forgot the exact number, right? And choosing the threshold to be 6 happens to be a good number that's getting rid of all of the false positives. Okay. So back to the two assumptions that we made. So some of these technical details about these assumptions don't really matter, but I wanted to explain the high-level ideas of why we need these assumptions to begin with. So the high entropy assumptions requires that as we roll out the sequence on the average sequence that the language model would encounter, and the corresponding next word probability distribution will satisfy conditions that depends on the moments, depends on the average L2 moments and L infinity moments of this sequence of PTs. And when things are perfectly random, so every token is generated completely at random, then we got 1 over square root of the cardinality of the vocabulary space. But when things are completely deterministic, then this Kasai parameter is equal to 1, right? So not surprisingly. So one example of this is you are like a football commentator, and then you see a goal, and you can ask the ChatGPT to repeat the goal for 500 times, right? And it's gonna commit and do exactly that, and there's no way that you can watermark this. And this high entropy assumption rule out pathological situations like this. The homophily condition is somewhat trickier, and it hasn't been discovered before our paper. So this is also somewhat specific to the green-red list style watermark. So the idea is that since this is Markovian kind of process, the language model keeps rolling out, and what you end up generating at the beginning may have some profound longer-term effect in the end, right? Especially if you are generating a very long sentence. So this gives you an example that if you increase the probability of certain tokens in the green list, and then keep rolling out the language model, you may end up getting a lower average probability of seeing green list tokens. That will be kind of counterintuitive, and will not give us the desired behavior of seeing the green list tokens. Seeing more green list tokens as in of today, right? So this example says that if you write a particular poem and then pick a random color, stay what it is, and then write a short piece without naming this color at all, right? So if it keeps going on and on and on, you'll generate this random color. In this case, it's blue, but then later it will never generate blue ever again, right? So the probability of generating blue in the downstream is going to be 0. So comparing to, suppose blue is not in the green list, right? Then the chances of generating blue at the beginning will be lower, but then it's actually higher, like if the sequence of the text being very long, and the chances of seeing blue is actually higher, right? So this is the other assumption, what we call the text homophily, that says that if you generate some words, then you're more likely to see the word again, like in the downstream, in the subsequent generated tokens. And this is really subtle, and you know, arguably, like it's not completely unreasonable, because if you say something at the beginning, it's more likely that you'll repeat that word rather than, you know, just avoid saying the same word again. Okay.
Here you were saying that this is ChatGPT.
Right.
You're saying that if a word appears a few times in the beginning,
Right.
ChatGPT somehow doesn't like to repeat the word again.
No, you specifically instruct ChatGPT to not do that. You're asking the ChatGPT to randomly select a color. If this particular color, blue, is in the green list, you'll have higher chances of selecting this color at the beginning, right? But once you select this, by conditioning on this event that blue is being selected, then the downstream probability of seeing blue the tokens being blue is lower, right? Comparing to the unwatermarked model. Yeah, this is what I do not want, and this is example showing that this thing could happen, and the homophily assumption rules this out. It says that if you select something at the beginning, the chances of seeing the same token is not gonna go down.
The question is that you're making an assumption that may not happen, right? Is this the case?
Yeah, I'm making assumptions that rule out some particular prompts.
Oh, that rules out some particular.
Yeah.
So if you do this optional step of the unique, maybe I misunderstood what it was, doesn't it make this problem better because you don't care about repetition of the tokens?
Yeah.
Okay.
Yeah, that's right. That's right. Okay, yeah, so the last property is our watermark being robust to edits. So this is very straightforward, right? If your tokens are unigrams, or it relies on only like a few tokens is just nearby, right? If you do arbitrary kind of edits, most of this statistical information that we average over is still going to be there, right? Adding or removing and replacing tokens is not going to change the z-score if the edit distance is bounded, right? So this is just a calculation that shows connects edit distance to how much perturbation there could be in the worst case to the z-score. So right, then if there is a particular margin that we use to detect this zy that we set ahead of time, then the watermark detector is going to be robust. Okay, so compared to the Maryland work, which depends on the previous token, ours is twice as robust. Because if you depend on the previous token, you can edit like every other token, right? So one edit would mean that you destroyed like 2 of the sensitive information, 2 of the information that can be retrievable. But in our case, every token is on its own, right? So it is, you know, in the very verbatim sense, like twice as robust compared to the previous work. And interestingly, the Aronson watermark can also be viewed as what we call this k-gram, based on this prefix kind of tokens. As I explained, it makes use of the Gumbo softmax trick by just adding noise to the logis before sampling. And the idea of the Aronson watermark is to make this Gumbo noise pseudo-random. So if this is actually generated from a watermark language model, then you can take you can look at the Gumbo noise and then just add up this additional statistical information that's coming from this Gumbo noise by conditioning on the generated content. Then you can get some kind of a similar thresholding function and similar score that you can calculate that gives you the correct detection. The main difference between the statistical watermark that we and the Maryland group had versus the cryptographic watermark that Scott Aronson came up with was that if you really have these fresh noises for this gumbo distribution, then you are not actually changing the language model at all. So in some sense, you have delta being 0, whereas in our case, we need delta to be non-trivial. Okay, so one may argue that why in the whole world do we still care about the green-red watermark? Not quite, because our quality guarantees work even after the green list is being generated, even after condition on the particular partition, right? Whereas I would argue that the Aronson watermark is something like really a deterministic generation if you condition on the pseudo-random function.
So can you tell us again why is having delta equal to 0 a bad idea?
Yeah, so it's a different kind of watermark that I'm not explaining in this talk, but it's due to the gumbo softmax trick, right? So this procedure of adding gumbo noise to the logits and then taking the argmax has the same distribution as the sampling from the exponentiated distribution of the logits.
And why is that bad?
It's not bad. It's good. It's good because it's not changing the distribution at all. It's bad because you are using a persistent gumbo noise instead of a truly random gumbo noise. Yeah, so if you run into the same prefix, and the next time the token is going to be, you're going to pick is exactly the same. Instead, in our case, we're going to actually randomly draw a sample with some fresh noise from a different distribution. Okay, so why does a unigram watermark work better than the k-gram watermark when you actually depend on the prefixes? So the Kirschenbauer et al. Focuses on k equal to 2, and Aronson's, he suggested using k to be equal to 9. So the reason why we find the unigram watermark to work the best is due to the robustness. So essentially, the robustness to edits property is proportional to the margin divided by k. So when you choose k to be equal to 1, it's a lot better than choosing k to be other values. And this shows up in the experiments as well. And interestingly, there are other attacks that, as a side effect, our watermark is robust towards.
On these comparisons to previous.
Right. This one?
I'm thinking of a possible disadvantage of having a single green list. If every student has 5 favorite words they like to use a lot, then
right.
1 out of 32 students be very disadvantaged. 1 out of 32 students will be potentially easily accused of cheating.
Unique would solve this for a little bit because it's only adding 5 pieces of information to the whole thing, which requires and the randomness of choosing this green list would just equalize everything.
But for any given randomness, maybe 1 out of 32 students will be majorly disadvantaged.
Yeah, but the unique is making sure that 5 words is not contributing significantly to the score. So even if the student repeat their favorite word for 200 times, right? If you use a unique version of the detector, then those words is only going to be counted once.
Okay, so there's a version of the detector that doesn't allow each word to have much influence.
That's right.
Okay.
Yeah, it actually also shows up in the bond with this Cmax and V.
Yeah,
right? Yeah. Okay, so there's this other attack that Scott Aronson talked about in his talk called the pineapple attack. So this is really interesting. So let's say that you can instruct ChatGPT to generate the homeworks that you're actually supposed to write, but instead of generating it directly, you ask the language model to insert a special token in between every other word. In this case, pineapple. And once it generates this modified version of the text, you can remove all the pineapples and then end up getting your essay. Okay, so this way it would destroy all the watermarks that rely on prefixes to decide on the green-red list or decide on the pseudo-random function. Whereas for the unigram watermarks, it still works. And with the unique, the pineapple is only contribute to 1 piece of information. Okay. There are other attacks that one of you have talked about, like translating into French and then translating back to English, or you can simply ask Llama to paraphrase to paraphrase the suspect text, and the watermarks are gone. Right? There's no real way like anyone knows how to solve this problem concretely. On the other hand, we find that in the experiments, like our watermark is also significantly more robust to paraphrasing attack using the state-of-the-art language model to actually paraphrase and evade the attack, compared to all the previous work. So we tried several data sets and 3 publicly available language model, and we run a bunch of experiments, and you can see that. So the first row is when there's no attack being conducted. You can see that all of these, in all of these cases, no matter what we set this true positive and the false positive to be, whether 1% or 10%, and the true positive rate is always 1.0. So you get perfect detection when there's no attack. When you are using ChatGPT and BART and other language model to paraphrase them, and you can see that the Kirschenbauer watermark took a hit that's more significant, whereas ours still get an F1 score of detection at, say, 1% of IPR with 0.9 and sometimes 0.86 across the board. Right? So even though no watermark is provably robust to paraphrasing attacks, when the sentence is sufficiently long, you can still get quite a bit of confidence in the detection for your detected text to be actually generated by AI.
Sorry, about the pineapple example, right? Isn't just increase the vocabulary will work for unique grammar? Like instead of saying pineapple, instead of fruits names.
Right.
Then the ChatGPT may found that it's easier to get the green in the fruits, right? So then the original text, the green will be much significantly less.
Right. Could you say your question again? So instead of using the pineapple,
To create what you have,
right?
and then say every word insert the fruit's name.
I see.
Apple, orange, or whatever. Then the mechanism, because it may turn out that it's easier to put more green in the fruit.
Right.
So ChatGPT will generate a long text.
Right.
Where the watermark is on the fruit.
Yeah, with a bunch of fruit names in between, and then the student can remove the fruit names.
The green are all there. Then the original text, because they are lazy, right? So the original text is the original text. So isn't that
Yeah. So I get it. So you can this is what we call the alphabet attack, right? You can ask the ChatGPT to generate in a sequence of the alphabet or the different kind of fruits, right? So it's no longer just pineapple. So as long as your choices of these tokens you inject is not specific to the green list, as long as it's independent to the secret key, then the impact of it is relatively low.
yes.
Yeah.
What I mean is that the ChatGPT may found that it's easier because you need the enforcement to have more green.
Right.
He may find it easier to have the green in the fruits. So the original text will be a mix of a green and red.
But you know exactly what those green tokens are when you detect.
Yes.
Right.
But then the person who submitted, he removed all the fruits. So then you have an equal number of red and green and less more green.
So the idea is that the fruits are greener.
I forced the ChatGPT to put the watermark in the fruits rather than the original text.
Oh, okay. Okay, so that's a different watermark that that you can create that is vulnerable to this kind of attack.
I mean, this attack is you try to have more green, right? You try to have more green, and then I as an attacker, I force you to put more green on the non-important part. Then I remove it. Then the important part will have an equal number of green and red. So and thus your detector will not be able to detect.
No, but then you violate the edit distance constraint.
Yes, I know that. Yeah. So
Right.
I did the edit distance constraint, but now this get back to the question. whether the security definition of this edit distance.
Yeah. Right. Yeah, it's not a very good surrogate for work, right? Because you can change a lot of text like at a flip of your mouse and keyboards.
So actually this leads to a
Yeah.
question of whether edit distance is a meaningful.
Right. It is what we were able to prove anything about, right? But in practice there are like many other attacks, like for example these paraphrasing attacks that are very difficult to get any handle on.
So you
Yeah.
see the question of why do we need to prove very secure as when so many other attacks?
Yeah. So yeah, that's a very fair point. And we'll happy to talk about that a little bit more like after the talk. Yeah.
So earlier, right, I asked that because I was saying I understand the edit distance constraint, but isn't it trivial to bypass the edit distance? I mean, it will violate the edit distance constraint.
Right.
Attacker does not care. Right? I mean, why does attacker care whether they violate your constraint or not?
Yeah, in some sense, if you violate the edit, right? In some sense, if you violate the edit distance constraint, you're changing the watermark text more significantly. And if you want to keep the text to be still like somewhat high quality, then you need to spend work. You can edit it and still get the original text back.
No, you don't get the original text back. You get something equivalent to original text back, right? But the equivalence has nothing to do with agreement rate, right?
Right. But in some sense, then you are relying on some external language models that's just as good,
I mean,
right? Then why are you using this language model to begin with?
Suppose you want to state a theorem, okay? And you can state a theorem in Gaussian waves, right? Like they're all equivalent to each other, right? But every single symbol is changed, right? So edit distance.
Oh, I see. Yeah, I see what you're talking about.
These are semantic attacks, right? But
I see.
of course they do violate the edit distance.
I see what you're talking about.
My point is that why does the attacker care?
Yeah, I see. So you, I think the question is that you can actually instruct the language model to instead of generate the token T, you generate the token T plus 1. You can encode this kind of mapping, right, in the language model generation, and it will generate something that you know exactly how to revert it back to the language. Right. Yeah, but the language model, so my response would be the language model is not trained to generate such modified sequences, and it will have a hard time coming up with something with high quality.
One simple example is that I instruct them to generate something that apply a substitution cipher. So he will output the encrypted text.
Right.
Encrypt it back, then all the thing is destroyed.
Yeah, this is easy to do if you get the text generated and then do the post-processing.
I teach him how to do substitution cipher.
Yeah, but without training with such text, the language model usually is not able to generate follows the instruction precisely while keeping the quality of the text just as high. Right.
We have done
Oh, you've done that?
substitution cipher just say
And the language model is able to, so that's very interesting. I'm, looking forward to hearing the details. So do you check the perplexity, and it's somewhat similar?
in fact that there's some work done by Hong Kong.
I see.
They want to avoid the firewall.
I see.
So they ask them to
I see. Yeah, that's interesting. Yeah, I think you can train a language model to do that, and it's going to do it really well, right? And it will be interesting to think about how watermark can still apply in these situations. If you have access to a good language model that is trained to bypass language models, and maybe you need to bypass the watermarks, and maybe you need to come up with watermarks that are somewhat tailored to these specific language models with a different purpose. All right. So let me wrap up. Okay. So we came up with a theoretical framework for dealing with watermarking for AI-generated text, and we showed that unigram watermark is in theory and in practice more robust to edits, comparing to other like K-gram watermarks, and also comparing to the Aronson cryptographic watermark, and this last slide, it's still very early phase of researching these problems. There are many big open problems out there, and how to define work and effort instead of using edit distance. So I'm fully aware of this is not the best surrogate for work. But in order for anything to be theoretically and formally written down, like some kind of a definition for work and effort needs to be defined and worked out, right? So what we did is provide a general framework that you can modify different pieces and then see if you can still get an algorithm that checks a different and hopefully more reasonable definition. So getting robustness to paraphrasing attacks and understanding the information theoretic limit of what can be done by any algorithm would be interesting research questions in this domain. All right, so let me stop. So I won't cover part 2 and 3. One of them is part 2 is about using the diffusion models and other generative image model to remove any watermarks that are invisible. Right, so we can prove that if any watermark is invisible, then you can just pass it into diffusion model and regenerate the image, and the destruction and reconstruction process will completely remove the watermark using techniques from differential privacy. And the last piece, part 3, is about we can use a similar idea to green and red watermark for services that ship the large language model, and for downstream tasks where people make use of to train a distilled large language model to hijack the traffic of the original language model, then the original developer of this language model that they're distilling from can take the secret key and probe the new services that are provided at half the price they charge, like $10 per month rather than $20, and then prove that their model is actually distilled, used my training data, use the data that's generated from my model. Okay, so for those who are interested in this, check out our papers and feel free to reach out. Thank you so much. I love your questions. Right.
Is that a major practical issue? And we try to get a really low false positive, does it stop working?
Yeah, increase the threshold. You can make this arbitrarily small. Yeah, because increasing the threshold logarithmically by log 1 over delta, you can make the false positive rate delta.
And in your experiments, could you really actually get like
yeah.
Yeah,
when there's no edits, when there's no editing attack and paraphrasing attack, then we actually get just 1.0 accuracy. There is no false positive at all.
Paraphrasing, it's like not really usable or like.
Right. With paraphrasing and I think what is nice about these things that this is able to take the subsets of the text and take truncations, and as long as they are subsequences of the text that is sufficiently like green, then the model is able to detect it. Then the detector is able to catch it. Paraphrasing, like I said, is difficult, right? It makes getting high confidence significantly more challenging. So that's why it's still an open problem to be solved.
So you can text students that are lazy, like they don't even bother. Use the copy and paste, you can catch those.
Yeah. Which is maybe non-trivial if it's part of their homework submissions, and they combine that with some of these other solutions that they've written themselves. Yeah.
Well, just a follow-up. At that such a low false positive rate with that small threshold, then how much would be the true positive rate? Would be able to detect.
Yeah. So as the length of the sentence to be detected gets bigger. Right, and both the true positive and false positive, the true positive rate will get exponentially close to 1, and the false positive rate will get exponentially close to 0. Yeah, but the threshold and the length of the sequence that needs to be detected is a function of delta. That there's an intrinsic trade-off over there.
It's a little bit counterintuitive. So if false positive goes down to 0, then you should miss some true positive samples as well. So true positive cannot be close to 1.
Yeah, but the thing is that the true positives, as the length of the sentence gets bigger, it grows like square root of n. Right? So if you set the threshold to be, say, 5 times the log n, right, then it is almost always over that threshold.
Right. You need longer sentences.
Right.
More questions? Jayon. Speak up.
Yeah, we didn't show this directly, but you can, in your detector, you can take all the contiguous sequences and then calculate the z-score. And then you can pick the argmax. So basically, you can do max pooling. And then you can take a union bound over all the contiguous sequences. And how many of those are there? There are n squared, right? And then you basically introduce additional log factors. So theoretically, there isn't an issue, but in practice, it does affect the quality of the detection and the trade-off between false positive and accuracy. No, you try out everything. You start from T1 to T2, right, and enumerate over all possible T1 and T2s. Yeah.
All right, so let's thank the speaker. Thank you very much.
Thank you.